Warm greetings, everyone. Education is the most powerful weapon which you can use to change the world. A famous quote by Nelson Mandela. With these words, I, Dr. Poonam Jain, your host and member of Executive Council, IAPT RC1, wholeheartedly welcome you all for the 10th online Professor Ved Ratna Memorial Lecture organized by Indian Association of Physics Teachers, Regional Council 1. I would first like to pay my sincere gratitude towards Sri Shruti Bodh Agarwal sir, son of late Professor Ved Ratna, and presently Deputy Director North, Directorate of Education, Government of NCT of Delhi. Sri Niti Bodh Agarwal ji, the second son of late Professor Ved Ratna sir. Sri Vishal Aksh, son of Sri Shruti Bodh Agarwal ji, for gracing us with his presence on this auspicious event. Also, we are delighted to have our special guest, Professor P.K. Aluwalia, sir, the President, Indian Association of Physics Teachers. Also, I would like to welcome our renowned speaker of the day, Professor Venu Gopal Achanta, the Director of CSIR NPL, New Delhi. The title for today's lecture is Metrology for Societal Applications. I would also like to welcome all the other distinguished professor members of IAPT RC1 and our virtual audience present over here. Before we begin, this is to inform you all that this session is being recorded and streaming live on YouTube. There is an important announcement for the participants that kindly post your queries and questions related to talk in the chat box only so that our coordinator can consider them after the talk. Attendance form will be shared at the end of the session, filling of which is mandatory, then only you will be entitled for the certificate. Attendance link will not be shared personally after the lecture, so I request kindly fill it during the session only. All the participants are now kindly requested to mute their mics during the whole session for the smooth conduct of this event. Now, without further ado, now I request Dr. Yogesh Kumar, the Secretary IAPT RC1, for the welcome address. Over to you, Yogesh sir.
Thank you so much, ma'am. Greetings to one and all. It gives me immense warmth and great pleasure to grace all of your presence in the 10th Professor Ved Ratna Memorial Lecture. On the behalf of IAPT, I, Yogesh Kumar, Secretary, IAPT RC1, welcome our eminent speaker, Professor Venu Gopal Achanta, Director, National Physical Laboratory, Delhi. We are delighted with the presence of Professor P.K. Aluwalia, President IAPT, Professor V.P. Srivastava, former President IAPT RC1, Dr. O.P. Sharma, ex-officio President IAPT RC1, our special guest, Shri Shruti Bodh Agarwal ji, Shri Niti Bodh ji, Vishal Aksh, son of Shri Shruti Bodh Agarwal, and other distinguished professors present here. I welcome faculties from various schools, colleges, universities from different parts of India, member of IAPT, TSSTF, and all other participants. With these words, on the behalf of entire physics fraternity, I welcome you all. Thank you so much. Over to Poonam ma'am.
Thank you, sir. Thank you for welcoming all the distinguished guests present over here. Now, I request Dr. M.S. Bhandari, the former Secretary, IAPT RC1, for the welcome address and introduction about the great visionary, Professor Ved Ratna. Over to you, Bhandari, sir.
मैम प्लीज मेरा वीडियो ऑन करिएगा.
Sure, sir.
मेरा वीडियो ऑफ है.
minute, sir. So now please try to switch on your video. Yes, sir.
Thank you, Poonamji. Good morning and welcome to all. Though most of our participants know about IAPT, it is customary and our objective to introduce you with IAPT, as some of the participants might be joining us first time. IAPT is a well-placed organization established by great visionary late Dr. D.P. Khandelwal in the year 1984. Since its inception, IAPT is continuously growing in terms of reputation and spectrum of activities. In every state, we have local chapters. IAPT RC1 is for Delhi and Haryana. We organize various different type of activities, keeping in view the interest, necessities, and current scenario in the field of physics and physics education. Ratna was an experimental physicist of repute. His contribution in establishing IAPT as well as to make it a reputed organization has been applaudable. To commemorate his contribution every year, we organize Ratna Memorial Lecture. Now, I would like to give a brief account of some of the major activities organized by IAPT at central level and at regional. IAPT conducts two national level examinations, NSEP, NGPE, and NSEP, which are linked to International Physics Olympiad. IAPT organizes various workshops for physics teachers and students at central level. IAPT is propagating Anveshika in different schools under each RC, aiming towards setting up National Anveshika Network of India, popularly known as NANI. IAPT organizes several workshops and activities based teaching learning in different schools and colleges. IAPT brings out two important periodicals, IAPT Bulletin and Physics Education. A student journal of physics named Prayas is also published by IAPT. IAPT organizes an annual convention which is open for all the members of IAPT. Sometimes national student symposia on physics are also organized to provide a forum for students engaged in innovative and investigative projects. Now at the regional level, Delhi and Haryana RC1, there are some activities, major activities we conduct regularly are workshop for physics teacher and students, orientation of teachers and students for NSEP and NGPE, conduct of NSEP and NGPE, organizing Professor Ratna Memorial Lecture, organizing regional competition on innovative experiments, organizing regional competition on innovations in computer for physics, organizing regional annual convention, celebration of days of scientific importance, undertake research on science teaching, development of resource material for physics teachers and students. Keeping in view the time constraint, I have given a brief account of the activities conducted by IAPT. Now I would request Yogesh ji to run a PPT on Ved Ratna. Thank you.
Yes, sir, I'm sharing. Just give me a moment.
Sir, is it visible?
Yes, Poonam, it's visible.
Sir, may I now stop sharing?
Okay.
Bhandari sir, will you continue now?
It's
Hello. It's over, ma'am. From my side,
over.
I have given the introduction. Now you can proceed with the program.
Okay, sir. Okay, no problem, sir. Okay. Thank you so much, sir, for the introduction about IAPT and about Professor Ved Ratna to all the members and participants present over here. Today, we are honored to have Professor Venugopal Achanta, the Director of CSIR, National Physical Laboratory, New Delhi, with us. Now, I request Dr. Seema Vats, the President, IAPT Regional Council 1, to introduce our distinguished speaker of today's lecture. Over to you, ma'am.
Thank you, Puna. It's a matter of great pride, and it gives me immense pleasure to introduce our eminent speaker today, that is Professor Venu Gopal Ajanta. He is the director of CSIR, National Physical Laboratory, Delhi, and he is on the LIAN from Tata Institute of Fundamental Research, Mumbai, where he is a professor in the Department of Condensed Matter Physics and Material Science. He is on the Senate of IISER, Behrampur, and IIT Delhi. He is a member of the Executive Council of Optical Society of India, Vice Chair of IEEE Photonics, Mumbai chapter, and member of Program Committee of Association of Asia Physics Societies, Division of Condensed Matter Physics. He is on the editorial board of the journals Scientific Reports, Frontiers in Physics, Encyclopedia of Applied Physics, and Indian Journal of Pure and Applied Physics. He is an honorary fellow of Meteorology Society of India and senior member of IEEE. His research interests are in nano and quantum photonics with over 130 journals publications. He is a genius in all respect, and his introduction would take a whole day. But we welcome you, sir. Kindly enrich us with your and enlighten us with your wise words and your talk. We welcome you, sir.
Thank you, ma'am. Thank you. So first, I would like to thank the IAPT team for giving me this honor to deliver this Professor Vedratna Memorial Lecture today. So I'd like to thank the team, Professor Ahluwalia, Dr. Seema Vats, Professor Sejwani, Dr. Saigal, Dr. Singhal, Dr. Poonam Jain, and Dr. Yogesh Kumar for giving me this opportunity. So what I thought is today I'll talk about my present responsibility, which is to promote metrology activities in the country. Right. So I'll talk about metrology. Metrology is a science and art of precise measurements, and how when we're doing these precision measurements, when we're setting up these precision measurements and making them available for the nation, the spin-offs or different applications which are of importance for the society comes up, right? So when we talk about NPL, people remember NPL for different reasons. Some people think NPL, I mean, whenever somebody says NPL, so they'll think of indelible ink, right? From 1962, when it was developed at NPL, so every single election, so when we get this ink mark, when we go for voting, right? So that's made at NPL. For some people, they think that like, okay, NPL is a preserver of the original Indian constitutions, right? So the enclosures which were made and then maintained, so these are carried out by NPL. For some others who are Marvel fans, we are the timekeepers of India, right? So uh, so we have the time standard for the India, and we disseminate it for various users across the country. Right. So this year is particularly important for all of us because we know this is the 75th year of independence. Azadi Ka Amrit Mahotsav, we are all celebrating. And we just completed the 79 years, and this is the 80th year of CSAR. And from NPL point of view, we just completed 75 years in January. Right. So what I'm going to talk about today is more about the National Metrology Institute, how CSR NPL is contributing to setting up the primary standards, what standards we have, and what is quality infrastructure. What does standards mean and why do we need them? Right. So I'm going to, in the first part, I'll be talking about it. And in the second part, I'll be talking about the CS, as part of the CSR family, NPL also contributes significantly to the society, to the industry, through the strong material science and environmental sciences group. Right. So I'll show you a large number of products, large number of spin-offs which come out from NPL during the last 75 years. Right. So every country has a designated institute called National Metrology Institute. Right. So, or National Measurement Institute. For India, CSR and NPL has been designated by the Parliament as the National Metrology Institute for the country. Right. So not just for the primary standards, even recently, like, so we are also designated by the Minister of Environment and Forest and Climate Change as the institute which sets up and maintains the standards for particle counters, monitors, pollution, measuring devices, etc. Right. So when you talk about standards, the first thing which comes to our mind is mass, a kilogram, which is a prototype. So this is a national prototype of a kilogram, which we have at NPL, which from which all the secondary prototypes are made. So I'll show how the entire standard scenario works in the country. Right. So this is a prototype called NPK 57, so which we have in the country. And this is the image of a platinum iridium meter bar, which is international prototype copy number 4, which we have in India. Right. So when we look at, sorry, one second. Right. Yeah, sorry. So when we look at this image, so we don't see much significance in this because it's just a rock or a hillock in which a cave or a small cavity has been chiseled out, and somebody would have been living in this long time ago, right? But if you look at an image like this, so what you see is a double decker. So there are 2 stories. So you have, what you have is in the ground floor, you have these very rectangular openings, which are entrances to the caves which are inside. And on the top, like, you have these pillars supporting the top level. And if you see, there is some shape and size uniformity is this in this structure. So not very impressive considering that we are making beautiful, tall, high rises these days. Only thing is, like, these are from Udaygiri caves in Odisha, so which are from a long time ago, right? Which are about at least 2000 years ago. Okay. So if you're still not convinced, we can go back to 7 BC to 1200 CE. You would go to Nalanda, for example. So you see these beautiful constructions where you have these different shapes. These shapes, like whether you talk about a circle or a pyramid kind of thing, like, so there is gradation, right? So and there are beautiful structures which are all made about 1,000 to 2,000 years ago, right? So if you look at the corner, the zoomed image here shows very precise size, uniform size bricks which are used in making these structures. So there is, I mean, even 2,000 years ago, we seem to have some uniformity in the measurements, right? Unless you have some prototype or some measuring tools, it's not possible to make uniform size, repeatable bricks, and from that, like, so these structures of very precise dimensions and shapes and curvatures and gradations, all these things, right? So if you look at units of measurements in ancient India, these are well known in the literature. So the Vedic literature, for example, talks about say 10 power 22, which is the cycle of the Brahma or the Brahmanda, goes all the way down to 10 power minus 7 of the in units of time. So this is a conch shell on which in the middle, like, so it's the gradations which are made on a conch shell, which is used as a tool for measuring length. And on the right side, we have some images of old Indian measuring units, right? So for different different masses, right? So at some point, like, we were measuring of the order of like microgram precision, for example, for gold and precious stones, right? So these are from the Kautilya's book. So there are 16 different types of balances which have been described in his book. So these are all from around 1 BC, from the Mauryan dynasty. So this is this is one of the weighing systems. So which works on the principle that the length of the pan and the weight which is inside that, the product of it is matched with the length of the length on this horizontal bar and the weight which is put, right? So the balance happens because length into the mass here, known weight here, is equal to the length times the weight in unknown weight in the in the pan, right? So these are all known for very long time, right? If you go to Egyptian standards, like, so most of the museums around the world have these the so-called Egyptian cubit rod. This is a scale which is from Egypt, and these, most of the museums have replicas of this. So if you see, like, so each palm is divided into 4 fingers, and each finger is divided, say, for example, on the rightmost, if you see, so that it's divided into 2 parts, 3 parts, 4 parts, and then it goes into very, very fine divisions, right? So they could construct these pyramids, etc., because they had these high precision measuring tools. Unfortunately, we did not preserve our standards so efficiently, right? So over time, there is an anarchy in terms of measuring different units. So different regions had different units, and even within a country or kingdom, there were hardly any uniform measuring tools. For example, even today, like, so if you go to buy flowers, he just uses a cubit, right? So these are all not so efficient ways of doing it. There is no uniformity, which is a major issue. So especially if you want to go for exports or to check the quality of the imports which you are getting, we should have a standard which is acceptable across the world. So most of the nations which are buying from us or who are selling to us, they should be accepting a uniform standards for mass, length, second, right? And then you have the voltage, current, right? So the amount of light, the candela, so all these things, the amount of material substance, the mole. So these are the 7 SI units, which are the basic units which every single country has. right? So the whole game of this metrology and making it acceptable across the world began around a year 1800 when the French developed the decimal system, right? And they have defined the meter as 10 power minus 7th, right? 1 by 10 power 7 of the length of the quadrant when you connect a line from the North Pole to the equator. So this is expected to be about 10,000 kilometers. So if you divide by 10 power 7, so that is 1 meter. But the problem with this definition is like, so how is it possible for anyone to go and measure this length accurately, right? This quadrant, length of this quadrant accurately, and then find the 10 power 7th of it, and then make a replica of it and transfer it around the world, right? So another thing is the kilogram was defined as the weight of 1 cubic decimeter of water, right? So these are again depending on the temperature, pressure, all these things. Like, so there can be some differences. There can be some variability from one place to another. So it came that like so. It came out that in 1875 there is a Treaty of Meter Convention happened, and then there is a CGPM which formed the International Committee for Weights and Measures, so which set up the committees which decide like so how we define the standards and how we should have these things. All these things are discussed in the CIPM, right? So and then CIPM has consultative committees for each of the measurable quantity. For example, acoustic, ultrasound, vibration, electricity and magnetism, length, all these things, every single quantity which we have to measure, there is a committee and which decides, which goes through different ways of measuring and comes up with a technical solution which is acceptable to everyone, right? So the CIPM in turn recommends to BIPM, which is the International Bureau of Weights and Measures in Paris. So and then from the BIPM, so the world is divided into 7 different metrology programs. So in India, we come under this Asia Pacific Metrology Program, right? Of which NPL in India is the National Metrology Institute for the country, right? So the way this works is like, so the BAPM decides like, so what the standard should be, and then this is accepted by all the NMIs, right? So for example, NPL is for India, NPL UK is for the UK, and NIST, which is well known, is for the is the NMI of America, right? And each of these NMIs will in turn provide the resources, provide the reference materials, provides the measuring standards to these regional reference standard laboratories, which are under the legal metrology department in India. Right. So in addition to setting up these primary standards and making them available down the line, eventually it has to go to the shopkeeper so that what he's measuring has also to be tested, right? So this all comes under the legal metrology. There are also standards which needs to be accepted and implemented in the country, which is taken care of by Bureau of Indian Standards, right? So the standard specifications and all that for components, for products, these are all worked out at BIS. The standards are defined there. And then the primary standards and traceability. Traceability means like, so whatever we are measuring in the shop, for example, so that one particular kilogram or the equipment which is using to measure, for example, 1 meter of cloth. These are all traceable to the primary standards, which are national standards, which are in NPL, right? So that whatever we are buying or whatever we are selling, not just within the country, but even outside the country, these are acceptable to the rest of the world. So this is the traceability, so that from NPL, so this is traceable to the rest of the world, right? So, so setting up and making these or disseminating these standards is a job of the NPL. And we also have this quality control of India now, which forms the backbone for accrediting labs, hospitals, etc., so that they go on making these calibration facilities. So whatever equipment is there, it need not come all the way to NPL, but either in the RRSL labs or in these private accredited labs. So these our instruments can be calibrated at. And these accredited labs are supposed to get the calibration from NPL. Right? So NPL also signed this mutual recognition agreement so that whatever we have at NPL, whatever standards, measurement capabilities which we have set up and maintain at NPL, these are acceptable by the rest of the world, right? All countries accept that, yes, so they are at par, acceptable to whatever we have, right? So the facilities which we have, the 7 SI units, the measurement capabilities which we have in the country are, for example, a meter, we have about uncertainty of say 20 picometers. Mass we can do with 4.6 nanograms. Time we have of the order of like 100 femtoseconds. The ampere we have about microamperes. Kelvin with say 170 microkelvin, right? So this is uncertainty in the value which I'm telling. So similarly for the candela and mole, we do not have yet, right? So we start with SI units, which are the base units from which we measure everything else, right? So then at NPL, we maintain these national standards, and then these primary standards, which are linked and verified, uh, I mean, continuously with respect to the national standards, right? So these are available at, for example, RRSLs or NABL accredited labs, and then from that you make these these working standards which go to these accredited laboratories, and then eventually you make these replicas for instruments and measuring tools which we use in the shops, etc. Right. As an NMI, so CSR NPL has multiple roles. We represent the country in the in the CGPM, BIPM, and other organizations. We are participants or members of different technical committees which make what should be the standards for the future. Right. So we're part of the MRA. Right. So we establish primary, secondary standards. We disseminate them and then provide traceability through established means. So then we organize, train people, right, and also provide expertise in the national and international committees and bodies, which makes these standards, etc. Right. At NPL, we have 7 divisions as far as metrology is concerned. So the Indian Standard Time, physico-mechanical metrology, electrical and electronics, environmental and biomedical, materials and device, and the Bharati Nirdeshak Drav, which are the standard or the certified reference materials, which many of us who know the materials point of view, like, so we know that somebody talks about niche standard material, right? A standard reference material is the trademark of NIST USA. Similarly, India has its own certified reference material brand, which is known as the Bharati Nirdeshak Dravya or the BNDs. Right? So how do we get this mutual recognition? How do we know that our measurement capabilities are accepted by other countries or at par or better than other countries? So what we continuously carry out is the intercomparison, right? You take one measurement technique or one measurement or one unit, for example, for the time scale. So we compare with many different countries in the world and get an uncertainty. So if somebody is measuring some particular unit, so what is uncertainty for each of the countries? So for example, India has 2.8 nanosecond uncertainty in the time which we disseminate, right? So that's one of the best available in the world. Similarly, if you want to talk about the temperature, the Kelvin, how precisely can we measure Kelvin? So the best in the world is about 60 microkelvin uncertainty. What we are proposing, and we'll go for peer review. So the APMP members will come and check our measurement capabilities and then certify, yes, we have, I mean, NPL India has this capability. So then we can say that, yes, I mean, we have 100 microkelvin uncertainty in measuring temperature. So currently we have 170 microkelvin, so that which we are proposing to lower it to 100 microkelvin, right? So this is for voltage standard. So we have reduced the overall uncertainty from 103 nanovolts to 60 nanovolts recently. the best uncertainty to compare is the record is held by Korea with 40 nanovolts. Right, in India we can measure with 60 nanovolt uncertainty the voltage. Right. So this is the resistance. For example, 1 kilo ohm we can measure with 100 parts per billion uncertainty. Or I mean, it's better than 100. It's about 80 parts per billion uncertainty is what we get. Right. So these are for force, pressure, and other things. So these are all just to show that when we compare with multiple, these are participating laboratories, as I said, like, so there is about 13 participating laboratories here. So each one corresponds to different country, right? So among all the countries, when we plot these intercomparisons, everybody measures the same sample is sent to every country, and everybody measures and then puts up their value with the uncertainty. And then that is accepted. Everybody cross-checks each one's calculations and analysis, and then says that, okay, we are okay with it. So if you see, so the Indian values are some of the best in the world, what we are maintaining, right? The same thing for UV and ultrasound power, for example, right? This is that's with establishing with the rest of the world what are the capabilities which we have. But once we have it, we also disseminate, we also make these standards available for the rest of the country. So for example, as I mentioned, the testing laboratories, right? So this is something which actually they go and provide services to local manufacturers or local shopkeepers, etc. So we provide the services to them. So these are all the industries which we cater to across, from defense to aviation, right? You name it. Like, so we provide these services to them, right? So this is state-wise because we are close to proximity effect. So Delhi has a large number of clients which we have, but even otherwise, what this plot shows is that basically this is directly correlated to the industrialization of each of the states in the country. So the more industrialized get, more meteorological services, all their industries come to us, and so on. Right, as I mentioned, so we are the timekeepers. In addition to being timekeepers, we also do additional things, right? So we work in for the future. So what NMI requires, so what our country needs, and make them acceptable at the global level, that whatever CMCs, what we call calibration and measurement capabilities. So we set these things and make them and compare them with the international peers, so that this is recognized measurement facility within the country. Right. So in addition to these works, like, so as I mentioned, we also make these reference materials under the Bharati Nirteshak Dravya brand, and our material science for basic and industrial research, and environmental sciences for weather, ionosphere modeling, and the monitoring stations. I'll show some examples of these, right? So how metrology activities are being catered to address specific problems of the society in, for example, energy, environment, health, security, in all these areas, right? So if we go way back, when we had these black and white TVs, the monochrome phosphor, and even for the color TVs, like, so the phosphors were first made in NPL, and then the technology transferred to Bharat Electronics Limited, Bangalore, and Samtel in Ghaziabad. This was way back in 1969, right? So when we talk about diamond cutting tools or something, so there is industry grade synthetic diamonds are needed. So NPL has developed the single crystals of synthetic nano diamonds. This is way back in the 1980s, right? So this is an indigenous single crystal puller from 1960s, right? So these are indigenous Digisonde and sorry, some blocks in there. Right, these are Sodar and Digisonde, which I'll be showing a little while. So these are set up in the 1970s and 80s. So there is a master control facility of ISRO was at 1980 to track satellites. So this has this phased array of wind profiling sonar. These are all developed indigenously in India. Right. In electrical and electronics industry, one major achievement in 1960s is the development of a large number of electronic components. These are ceramic based components which were all spun off to have the Central Electronic Limited CEL, which was set up at Saibabad in 1974. Right. So very recently, in December 2021, Honorable Prime Minister has inaugurated the facilities at Regional Reference Standard Laboratory Varanasi. So for this, we have developed completely indigenous, semi-automated testing facility for blood pressure monitors as well as clinical thermometers. Right. So these DC high voltage testing facilities with 1 kilovolt to 100 kilovolt range with 20 to 100 microvolt uncertainty, which we have. So this is generally the power lines which we are getting from power stations to our homes, and energy meters what we have at home. So all these are calibrated and tested at NPL, or the facilities are provided so that like this can be tested. So these are some of the BND's reference materials which are available. So we're also exporting these things to many of the SAARC nations as well as neighboring Asian countries. Right. So this
Sir, you are muted.
Yeah, I don't know how. Okay, ma'am. Right. So this is spray forming unit which was developed at CSR NPL. So these was used for making these strategic alloys of aluminum and magnesium. These are used in INSAT and PSLV rockets as well as advanced light helicopter, uh, uh, which is developed indigenously in India. Right. So these are carbon composite materials which were developed for the cone, the front cone of the Agni missile. Right. So these are for characterization. You need good X-ray diffractometers. Nowadays we buy everything, but in the 1970s and 80s, these were actually an XRD, 5-crystal XRD with the best resolution. In one of the best resolutions in the world was available at NPL. Right. So these are superconducting magnets which were developed at NPL. So now the technology is with IUAC, Inter-University Accelerator Center. So these are the centers, the Maitri station in the Antarctica. So there is a SODAR which is still maintained by NPL. So we collect continuously the data from there and then try to monitor the weather conditions and also model the ionospheric, which is about above 50 kilometer height. So we do modeling of that. Right? And this is a cesium fountain which is developed as an atomic clock within the countries. This is one of the 6 or 7 countries in the world who had this technology. So we have this bank of cesium clocks now. These are commercial ones on the right side. So these are biomedical device standards which we are working currently. For example, in January, Honorable Minister has dedicated to the nation calibration facility for defibrillators, which are used for reviving patients by giving shocks, right? And also infusion pump device and the infusion pump analyzers have been set up and made available to the country, right? So this is a wind tunnel facility to test particulate matter 2.5 micron or 5 micron or 10 micron. Like, so you need to precisely measure the particle sizes. So the samplers which are used, they need to also be calibrated and tested whether they are doing measuring right counts and right or not. So this is the PM 2.5 sampling system, which is used for calibrating these commercial samplers. These are carbon composites. This is, for example, Elizarov fixator, which is used for limb support. So these are compact fuel tubes for high temperature nuclear reactors. This is in collaboration with BARC. Okay. So these are, for example, completely indigenously made, I mean, from the carbon paper. So these BMFC fuel cells, right? So these are released recently in 2019. Is Honorable Prime President and the then Minister of CSIR, right? So Vice President of CSIR. These are color shift pigments which are used in currency notes. We made these, and we're trying to commercialize this technology transfer so that like this can be indigenously made pigments can be used instead of spending thousands of crores each year in buying these pigments from outside. So another important work which we do is waste to wealth. The plastics for example, current work which is going on is to make these pavement tiles and the solar cells, the solar cell waste, both for reusing the silicon as well as extracting precious metals out of these discarded solar cells, and agricultural waste to particle boards. Right. So these are techniques which are developed and transferred to industry. The technology is transferred to industry so that it's available for people. So this is another very important thing, which is this is called the free air phase facility. This is only the second nation in Asia to have the facility. So to study the influence of atmospheric carbon dioxide. So as the pollution levels, all these things are increasing, the carbon dioxide is increasing. How that increased atmospheric CO2 is affecting the crop. So this is being studied at IARI. So this is basically what you do is you make these local areas where you can control the amount of carbon dioxide which is there, and then you can study the crop yield and other things in a smaller test regions. Right. So these are again monitoring station at Palampur. So this is a high altitude monitoring station for measuring the background pollutants and other things in the country. This is in Himachal Pradesh. Right. So more recently, to address the COVID time, so NPL has developed a UVC based room disinfection system, so which is good for hospitals. This has been tested to kill 99.99% virus and a wide range of bacteria. So that is useful not just for office rooms, classrooms, etc. It can also be used in hospitals. Okay. So this is a standalone unit which is available commercially now. These are various certificates for electrical safety to viral and bacterial efficacy of this device. Right. Some of the ongoing major projects which we have are in line with the Government of India initiatives to make Atmanirbhar Bharat, quality infrastructure in the country. Right. So all these things. So for example, we have set up LED testing project. So you have this Ujala Yojana where LEDs are promoted by the government to reduce the consumption of electricity, right? So what is the quality of the LEDs which we are using at our houses, right? So whatever imported or locally made, now we have facilities where we can test and certify wide range of LEDs of different colors, different sizes, different powers. We can do all these testings. Right. So in the we are also setting up regional time standard centers with ISRO. So these are 5 centers across the nation, and we're also currently working on testing and calibrating pollution monitoring equipment. So this is another major project which we are undertaking. Right. So this is a photovoltaic primary standard for catering to the growing solar energy industry, whatever is the local industry. The solar cells which are made or imported ones, so there are no standards to calibrate or test these solar cells currently. So we are working on setting up these standards, right? So for future, like, so for quantum is very important, whether you want for quantum computing, a quantum computer, or a quantum key distribution, which is for communication safety, safe and secure communication of information from one place to other. So quantum standards are very, very important. So we are working on setting up these standards for single photons. And we have a strong focus on developing quantum metrology standards to take care of these new definitions of SI units. So in 2019, world over, everybody, all the countries have accepted that now all the SI units, instead of having kilogram as a prototype, or that length bar as a meter standard, which I showed in my earlier slides, instead of that, like, so can we link the kilogram to, for example, Planck's constant, the length, for example, to interferometry based measurements, right? So all the 7 SI units are linked to fundamental constant, Boltzmann constant, right? So all these are linked to the fundamental constant, so that the uncertainty is reduced in the overall measurement to the ultimate limits, push them to the limits, right? So this is the LED calibration facility which is set up now. This is a complete photobiological safety testing of light sources is also possible, right? So this is some example of how we generate single photon sources. This is my own work from TAFR. So we put these single nano dots inside these so-called hyperbolic metamaterials. So if you have a homogeneous medium, so you can put the K space is spherical in shape. But if you can make materials such that they're not metallic or not insulating all over, but say in 2 planes, so in X and Y direction, in plane direction, they are metallic, and in the third direction, they are insulating, or vice versa. It is metallic in the third dimension, and in plane, it's insulating, right? So you can design and make these materials at will. So these are the metamaterials, so which you can generate, design, and make them in the laboratory for different applications. So we designed these structures in the central zinc sulfide, for example. So we put a single nanoparticle of 2 to 6 nanometer in size and look at its emission. So this is the structure which we have on substrate. We have this structure of alternating layers of dielectric and metal. And in the central layer, we put a single nanoparticle and then put a patch antenna on top, and we get directional emission. If you want to get a single photon, so there's a lot of background which comes from different different areas, or different possibilities are there. This can be scattered light, it can be light emitted by fluorescence, right? So we need to check each of the materials for which one is best for making these structures, and also efficiently couple a single photon coming out from one single nanodot into this medium, and then take it out into the free space so that we can use it for different applications, right? So we use this antenna to couple from this hyperbolic metamaterial to far field. So that's what is shown here. So the light which is coming from the center from this nanoparticle is coupled by this combination of hyperbolic metamaterial and the antenna patch antenna on top, so that you get a very directional emission of single photons, right? So we showed 200 times enhancement in emission, and 40% of the photons which are emitted by are collected in our measurement geometry, right? As I said, the background photons are very, very important. So we studied a wide range of materials, metals, and insulators, and then embedded nanoparticles, quantum dots, or for example, these nano diamonds inside them, so that we can check which is the best material, which help us get highest efficiency single photon emission. So how do we know whether we have a single photon or not? So what we do is we put a beam splitter. So if it is a single photon, it can either be reflected or it can be transmitted. It cannot be both reflected and transmitted because it's a single particle, single photon. So we measure the probability of finding photons simultaneously at a given time in two detectors which are placed in the reflection and the transmission mode, right? So that probability will be 0 if we have a single photon, right? If we have, for example, 0.5 probability, which means that we have about 2 photons which are from the source, coming from the source, right? So this is, we showed that basically hafnium oxide is very good material, which will help reduce the blinking or the problems with the quantum dots and help us get single photons out of these structures. So currently at NPL, we are looking at making these superconducting nanowire based single photon detectors. So these are structures which are, the device structure is like this. These are meander-like structures. When a single photon falls on this, either it gets absorbed or it heats the locally, and then the superconducting nature is gone. So it becomes a normal metal, because of which the current which is flowing gets reduced, and then you can get a voltage pulse out of it, right? So we use that principle to make these single photon detectors based on superconducting nanowires. Just to summarize, to meet the growing demands of the young aspiring population, so we know that we have a USD 5 trillion economy target for the government. But to meet these targets, we need quality infrastructure within the country. We need facilities to make sure our products are good enough for export, acceptable for export to other countries. Right? At NPL, being the National Metrology Institute, we set up and disseminate standards across the country. And by continuous interaction with Bureau of Indian Standards, the Quality Council of India, and its constituents like NABL, NABH. So we make sure that these are spread across the country, right? So we have just completed 75 years in the service of the nation, and we are looking to meet the challenges to help the government make our nation stronger, better, and self-reliant. So one of the crucial things is that, so we have to bring global solution to solve local problems and address local problems at local level. So we cannot expect somebody else to solve our problems. So we bring, for example, waste recycling or setting up future primary standards for the country. At NPL, we are tuned in to the needs of the nation, and our efforts are in that direction. Right. So these are acknowledgements to all the CSIR NPL staff, the SNSPD team, and the TF are my student and visiting Professor Farazana. Right. Thank you very much.
Thank you so much, sir. Thank you for enlightening the audience with such a knowledgeable lecture. It is indeed excellent and elaborate information about meteorology and its application in society. Thank you, sir. Now the session is open for the questions. So first question is by Dr. Dhirendra Shah. Can the CSIR NPL organize a workshop for physics faculties or the PG teachers?
Yes, certainly, ma'am. We can, and we regularly organize these training programs for different stakeholders, whether it's industry or visiting students. So we can certainly do it. So if IAPT or anyone can write to us, and then we can organize them.
Okay. So second question is by Mr. Bala Nitharan. In physics, there is a concept called art integration projects. Kindly throw some light on it and also kindly enlighten us. Is there any, yes, same question. Is there any workshop conducted by CSIR and BL for the same?
Okay, I never heard honestly. What is this art of?
Art integration projects.
Art integration project. I never heard of it, ma'am. So I'm sorry.
Okay, no issues. No problem, sir. Sir, another question is by Miss Mohini Nagpal. Which software is used for obtaining curves, and how do you find uncertainty in fundamental units?
Right. The plotting software, there are many commercial softwares. For example, popular ones are Origin or Sigma Plot, or you also have the freeware. For example, you can look at CERN. For example, CERN has packages which are used for plotting as well as data analysis, etc. Right. So the uncertainties are measured with different ways. So when we talk about meteorological uncertainty, uh, so we have to take uncertainty budget of every single equipment which is used in the measurement. We use a voltmeter or we use a current source or something. Like every single equipment, we need to measure what is its resolution, what is uncertainty with which it is measuring the value. And we add all those things as we need to take care and of each and every equipment which is contributing to the uncertainty. So typically our measurements, or when we say there is a CMC, the calibration and measurement capability, it takes 2 to 5 years to say that, like, yes, we have built this new CMC for the country.
Next question is by Dr. Rakesh Kumar. Is NPL is working on developing earthquake forecasting system?
Yes, there are people working on earthquake modeling. So there is Dr. Upadhyay who is working on correlating earthquake monitors which are on the ground, and for example, the ionospheric monitoring. So how the ionosphere, which is 50 kilometers away, up in the sky, with the ground-based monitors, like, so is there any correlation between the earthquakes and the modifications which are happening in the sky? So yes, I mean, there's work going on.
Okay. Next question is by Mr. Pramod. Can you elaborate instrumentation technology which is available for startup?
Instrumentation, so this one thing which I'll be honest, has to develop much more in India. We are dependent and we continue to be buying equipment, high-end equipment from outside. So unless we start at some point, the startups are very good point, like, so you can take up this challenging problem. Like, so I'm sure, like, so you talk about a simple voltage source or a current source, we tend to buy from outside. You have these preamplifiers, very good preamplifiers from Lakeshore or somebody, like, I mean, so we tend to buy these things. These are simple electronics which we can do within the country. Startups can contribute. We can work together and see, like, how to take these things forward.
Okay, sir. Next question is by Ms. Sudeshna Ghosh. Is NPL working on any project on reducing global warming at grassroots level?
So we have 2 or 3 projects. So one is about the particle monitoring, as I mentioned, right? So this is about the calibrating the particle counters and other things, the sensors, etc., calibrating them and testing them, certifying them. Then the second aspect is the monitoring of the pollution itself, the background pollution, as I mentioned. So we have these field stations at Palampur as well as in Antarctica. And in addition, for example, in the Delhi NCR region, we carry out a project. This is a DST funded project where we looked at how many people are using, for example, what kind of fuels, right? So there are quite a few plants and trees and coal, which is still being used in Delhi NCR area. So we collect these samples from households and different industries. Then we test at NPL, like, so what are the byproducts of these fuels? So we have comprehensive data on that. Right. So these are not directly related to the point which is asked, but these are all the indirect inputs which go into improving our environment.
This was the last question, sir. Rest, I can see a lot of appreciation. Sir, one more question by Dr. Vikas Mittal. Dear sir, to increase interest in physics, can you plan a visit of NPL for school students?
Yes, certainly. We do have this continuous thing where once in a week we can allow school students, right? We have open house once in a year. We have Science Day celebrations. We have our Foundation Day celebration. So we allow students, we specifically interact with about 170 schools across Delhi NCR area. Right? So we conduct competitions to them. We invite them to participate in various activities. So any school interested, yes, certainly we can arrange a visit.
Thank
Sir, I have a query actually. That you talked about BNDs in your talk. What are these actually? These BNDs? What kind of
So,
products there?
so it's basically uh, gold, right? That's the simplest to understand. So I'm just taking up that. So the gold purity, how do we know whether we have we are buying the good quality or not? So we have this hallmarking, right? So, but how do you check whether the gold which is being sold is correct or not? So there is always a reference material with which we test the purity of the gold. So that reference material against which we do this check. So that's a BND right now. Similarly, silver, right? These are for precious. It's just not, I mean, even for rice, for example, right? How much heavy metals are there inside the rice, right? So we make these reference materials with very specific quantities of these heavy metals. So this is took about 3 years actually cultivated within NPL because nobody wanted to collaborate. So the cultivation was done at NPL, and then these rice samples were made with specific quantities of heavy metals. Right? So ferrous, non-ferrous metals, cement, right? Oil, for example. So we make reference materials for all this.
Okay, so that's very good. And that's the second thing I would like to inquire about. Like if IIPT wants to organize some training workshop on instrumentation, let's say we have a batch of after screening 25 students and teachers combination, and they can do some kind of instrumentation like making of a furnace or making of simple instruments. Is it possible with collaboration of this NPL, and can they provide a venue for this, or we have to arrange on our?
We can certainly take this up, and we can certainly provide the facilities and the training which we can do this. Right.
And is there any particular time in a year that you can provide these facilities, or all over the year we can have
So
any time?
our HRDG Human Resource Development Group, like so, is very busy throughout the year, ma'am. So they do continuous training programs. They do skill development courses. They are actively teaching students, and right. So this goes on, and we can find a mutually convenient time, right?
Okay.
And we can organize.
Definitely we'll come back to you with instrumentation training, and I hope it will work out soon, very soon. Thank you, sir.
Yes.
Thank you so much.
Thank you, sir, for accepting our invitation and sparing your time for sharing your knowledge.
Thank you.
Now, we are delighted to have Shri Shruti Bodh Agarwal ji, the son of late Professor Ved Ratna and presently Deputy Director North, Directorate of Education, Government of NCT of Delhi. I would like to invite him to share his reminiscences about his father. Over to you, sir.
Okay. First of all, I would like to correct you. I have retired in February, so I'm no more in service and enjoying my retired life and doing various things.
Sure, sir, I noted it down.
So about my father, well, I have a few thoughts for you. My father aspired to invent new experiments in physics. And he went to UK for the first time in 1963, and he visited about 35 schools there. And there he was very inspired by the way the teachers used to encourage their students of grade 12 or even 11th grade to innovate and make new experiments in physics. So then that was the thing when he took up that career. And he was very passionate about IAPT also. And he conducted making workshops for students and teachers. And he was very inquisitive about new knowledge. Let me share he first drove a car at the age of 62 years, and that too an ambassador car. Hello?
Yes, sir, you are audible.
And he was very critical about the sad state of science education in our schools. I remember he went to a CBSE some curriculum committee, and he was very the year CBSE started to pass the students with combined marks. He was very critical about that, because that way the practicals are being neglected. And he joined computer education at the age of 78 years. So that way he was very passionate about learning. And one thing that we can learn from him is that we should always strive to get new knowledge. And that is at least what I am doing myself right now. And thank you for giving me this opportunity.
Thank you, sir. Now I request Professor Ahluwalia, sir, to present the concluding remarks. Over to you, sir.
Thank you very much. I'm delighted to be part of this lecture. Thank you, Professor Venugopala Chanta. You gave a wonderful lecture. And I think you were talking about the core of physics, in fact, which involves measurements and how accurately and precisely we make measurements. And you emphasized that in your lecture. It was a delightful lecture. And I think you gave many thoughts of conducting some projects also by the students. In new education policy, there is a lot of talk about, collaboration of the schools and colleges and universities with national labs. And I hope NPL will definitely lead in that particular direction. There is another thing which I would like to really request is that kindly think of creating some real-time labs which people can, join and conduct their experiments from remote places, particularly at undergraduate and postgraduate, in education there. I think that will be a wonderful contribution of the NPL in that particular way. Another thing which I would like to say is this, that I have very fond memories of Professor Ratna. We in fact spent 3 days in Bangkok in a hotel where we had gone together to attend a conference on physics education research. And I could really feel very intense passion which Professor Ratna had for education, particularly regarding the importance of experiments at school level. And at that time also, he was almost in his near 80s when he had went there to join that conference. And I think that was a very interesting learning experience also for me. And we remained in correspondence after that also. And I know that he used to write in longhand, all his papers, will draw diagrams very passionately and share for comments. That was great of Professor Ratna. And he was one of the founders of IAPT, I would say. He was part of that team which Professor D.P. Khandelwal actually gathered all around the country. And he remained committed to the work of IAPT also. And he was a regular participant in the annual conventions of the Indian Association of Physics Teachers. And I think this lecture particularly is a tribute to this great visionary, because he was very passionate about experiments. I think I have never come across anybody who would start with small things and, excite students. His telescope workshops actually were a wonderful way of doing that. He also had developed a laser kit of his own when lasers were not so easily available. I think that is again something reminds me of that. If you have the will, you can do it with very meager means also, which can be uh, very impactful as well. So I sat in this lecture fully, and because it was also my way of paying my respect to Professor Ratna, and I also congratulate Regional Council 1 from Delhi and Haryana, that they are continuously going ahead with very imaginative programs once again. Congratulations, ma'am, Dr. Seema Watts, Dr. Poonam, Dr. Arora, Dr. Bhandari, and my greetings to the family of Professor Vedratna also. And I think you were very fortunate that you had such a great father, and you are following in his footsteps. That's one of the best things which any son can do. Thank you very much once again, and thank you, Professor Venugopal ji, for sparing your time for us today. And we hope that we will have many more such occasions to enlighten IAPT fraternity, which is having more than 10,000 members throughout the country. And I think NPL is, whenever one looks at NPL, it reminds us, sir, not only of that indelible ink, but it reminds us of very many other things also. That who were the leaders who actually created this and were passionate about it, and has led basically that infrastructure of research all across the country. So once again, thank you very much, sir. It was very lucid and fluent lecture. Enjoyed it thoroughly.
Thank you. Thank you.
Thank you so much, sir. Now, at the end, I request Dr. S.K. Singhal, the Treasurer IAPT Regional Council 1, to propose vote of thanks. Over to you, sir.
Thank you, Poonam ma'am. A very good afternoon to one and all present today. First of all, I would like to thank Honorable Professor P.K. Ahluwalia sir, National President IAPT, Professor P.P. Srivastava, former President of IAPT RC1, Dr. O.P. Sharma sir, Dr. Seema Watts, President IAPT RC1, all respective guests, IAPT members, and all participants. It is my privilege to have been asked to propose a vote of thanks for this great occasion in the 10th Professor Vedratna Memorial Lecture on Metrology for Sociological Application by Professor Venugopal Achandra sir, Director CSIR NPL Delhi, Dr. S.K. Singhal, Treasurer IAPT RC1 Delhi Arena, on behalf of IAPT RC1 and entire team and my own behalf, extend a very hearty vote of thanks to Professor Venugopal sir for presenting wonderful lecture and sharing the useful information that is very valuable for all of us. I also like to thank Dr. Mohan Singh Bhandari sir, who always present us, Dr. Yogesh Kumar sir, who is the Secretary IAPT RC1, Sujan Singh sir, Vice President IAPT RC1. We also have R.K. Tiwari sir, the former Vice President, Professor S.K. Sejwani sir. He always present with us in all the programs and motivate all of us. He's younger than us, all of us, because he always motivates all and our entire team. We also have Manoj Kaushik sir, and we have the family of Professor Vedratna sir, I learned many things from Professor Vedatan. Still, I have one kit that was made by Professor Vedatan, the black box, the optical kit that was made by Professor Vedatan. Still, the kit used in many schools, and in the kit, he put all the small things and a booklet that was given by him. Still, we are using and we are showing to the students. So we are, when we recall Professor Vedatan, I remember the day when I was workshop organized by him. He first explained all the experiment, then he told us do this all the experiment in front of me, then only anybody will be allowed to go. So not only delivering the lecture, he emphasizes for a participant to do the experiment, show the result, then only he say okay. So we are thankful to the family of Professor Vedatan sir, Shruti Bodh Agrawal sir, his son Niti Bodh sir, and his son Vishas. We also have our IPT member Vikas Mitra sir. So I would like to express my gratitude to all speakers and all the team members of IPT for this presenting wonderful session today. And I especially thank to our president, Dr. Simawat, for his and efforts for organizing such wonderful program. Thank you all.
Thank you, sir. Before signing off formally, I once again thank the speaker for enlightening the audience with his wide spectrum of knowledge. I put my sincere gratitude towards all the guests and thank them for raising the occasion. This event is not completed without mentioning a big thank you to our participants for making it a great success. The attendance link is already shared in the chat box. Please fill it during the session. Thank you everyone for joining us. Thank you for being a part of this lecture. Have a great day ahead.
Thank you, Puna. Thank you, sir, for excellent talk. And now I think it's time to wind up the things. So
Thank you very much.
Thank
thank
you.
you. Thank you,
sir.
Ahluwalia sir. Thank you, Shruti Bodh sir. Thank you,
Thank you.
everyone.
Thank you, everyone.
Thank you, Poonam ji, and
Thank you
thank
very
you,
much.
Sina ji, Bhandari ji, and Singhal साहब.
Thank you
Singhal
so
साहब,
much, sir.
आपकी ना बैकग्राउंड बहुत अच्छी थी, बहुत पसंद आई.
Thank you, sir.
Just beautiful. It should be like
अगली
that.
बार हम सभी ये लेंगे सर का बैकग्राउंड जो है वो हमारा भी होगा अगली बार.
Everybody will use the same background.
Yes,
IPT.
yes. Yeah. ठीक
Thank
है
you,
sir.
sir. Thank you so much.
So, bye.
Bye. Have a